All right. So you should all see the machine learning k-nearest neighbors splash screen. Ping me if you don't. And all right, second part of the day, machine learning, or a very, very brief introduction to machine learning and to k-nearest neighbors. All right, here we go. So, what is machine learning? So what we just did was we wrote some kind of a program which did something. And it's never going to be the case that the program that you wrote gets better at playing Connect 4 after playing a certain number of games, or so on and so forth. The idea behind machine learning is that instead of just writing a program to do something, you write a program which has the capacity to learn. The program itself starts out in a sort of blank slate, tabula rasa, doesn't know anything, learns from a bunch of data, and then is able to do something. Right. So in one stage, you just write the program and then you're done. In the other one, you write the program and then you train the program, which means it's a bit more laborious because when you're writing a program, you usually have like bugs, and you have to go back and forth between like trying to use it and writing it. And there's just sort of like more a greater number of dimensions where things can go wrong when you're doing machine learning. Anyhow, it's easiest to really understand what this means when we go over the kinds of machine learning. That will give you more of a feel for it. And there's different ways to divide machine learning, but if you divide machine learning by the kinds of data that you learn from, because you can also divide it in other ways, of course. But if you divide it by the kinds of data that you learn from, then you get supervised learning, unsupervised learning, and reinforcement learning. And this is sort of the sort of typical way of dividing up machine learning, even though it's when you get down into the weeds, these sort of start to bleed into each other a little bit. So what are these? Well, supervised learning, you're learning from data that includes an example of an input and a correct output. The algorithm learns from this information to map from a previously unseen input to a correct output. So concretely, what does that mean? So we have image classification problems, for instance, such as in the ImageNet competition, right? So like I show a neural network a bunch of photos of like dolphins and say this is a dolphin, a bunch of photos of ships and I show this is a ship, a bunch of photos of like mushrooms and say this is a mushroom, and it learns to classify images correctly from that. You can also do things like move prediction problems, right? So I could show you a chessboard or a Go board and say, it's Black's move. What do you think Black probably did next? And you can get really surprisingly high rates of being able to guess that correctly. I think AlphaGo was able to, I think the sub part of AlphaGo, which did supervised learning, was up to like something like 50% in move prediction for Go. And then of course you also have stock market regression, which takes place everywhere in New York City, where you're just trying to predict what the price of something will be 10 seconds, 10 minutes, 10 hours, 10 days from now. And of course it's very easy to, well, okay, I was going to say it's easy to train. It's to a certain extent easier to train algorithms to do this because you've got lots of data to learn from, namely all of history, but it's very hard to make it work well. So those are instances of supervised learning applications. What are some algorithms for this? So some supervised learning algorithms include k-nearest neighbors, feed-forward neural networks. All of the image classification I mentioned is done with feed-forward neural networks. There's also recurrent neural networks, which can be used for problems like given audio, can you transcribe that audio to text, things like that. Recurrent neural networks tend to be used for things like time series, so you could also use those for predicting stock prices and things like that. So you have support vector machines and decision trees as well, which are both kind of interesting and cool, and I encourage you to look into, but I'm not going to really have time to talk about. If the one we're going to do for this exercise is k-nearest neighbors, but if you're interested in something that's like one level up in difficulty after that, decision trees are relatively easy to program, so I'd encourage you to start. You could look at that. But yeah. So yeah, those are some of the algorithms you could look at. All right, so that's supervised learning. What's unsupervised learning like? Well, in supervised learning, where like you're learning from data, where you're given an input with an output. In unsupervised learning, you just have the data. You don't really have any output. And so from this, you would just learn to sort of characterize the structure of the data in some way. And you could characterize it by saying, well, these are clusters in the data. You could characterize by saying it, this data can be compressed. Here are like the principal components of the data. But you basically learn sort of to characterize the probability distribution where the data came from without really learning like a correct output. That's a little bit vaguer, I realize. So you can use this for things like dimensionality reduction. So if you're given a bunch of data and you're told to say compress the data with minimal loss of detail, that would be something that unsupervised learning can be used for. You can do cluster analysis. So if you were running some kind of e-commerce website and you wanted to know if like maybe there's different sort of kinds of customers that you have, right? Because you might have one kind of customer who comes in to sort of browse. You might have one who comes in with like a very definite goal, and maybe like you'd want to have different kind of advertising techniques to approach each of these different kinds of clusters. But before you do that, you need to find out if there are clusters. So you could run an unsupervised learning application on the behavior of a bunch of different customers and sort of classify them into, you could find the groups into which you could classify them, which you could then use for further processes. Or you could build like a sort of probabilistic model of things, such as with the Voynich manuscript, which I'm not going to explain if you haven't heard of it, but you should look it up in Wikipedia because it's really cool. Some algorithms you can use with this are k-means clustering. You can use neural networks again with autoencoders. You can do principal component analysis or single linkage clustering. Yeah, pretty much. If I'm going too fast, somebody stop me. If you have any questions, things I'm not saying don't make sense, again, just feel free to stop me in the middle of a sentence. All right. So that's unsupervised learning. And finally, we have reinforcement learning. Reinforcement learning, generally speaking, is about how to take actions in an environment to maximize some kind of a reward. So it's like Minimax, except it learns from experience and is generally far more flexible. So examples of reinforcement learning applications include playing Atari, such as is done by Google DeepMind, playing Go, with AlphaGo made by the same. And use sort of more interesting meta models, such as there's like, I don't know, a few months ago, and still now really, there's a spate of learning to learn models everyone is trying to publish, where basically you use a reinforcement learning algorithm to create like a feed forward neural network algorithm, which you then use in supervised learning. And the reinforcement learner gets rewarded if it makes a supervised learning algorithm, which does really well on a particular problem. And so I don't think people have really sort of hit like a, how to put it, I don't think people have really cracked open like the center of making learning to learn models in the sense that it'll be like intelligible and useful to everyone. But they found some like state of the art is now set in particular supervised learning applications by models which were made from reinforcement learning algorithms. So that's a really interesting application, I think. It's hard to summarize reinforcement learning algorithms because in some ways they're sort of high level and you sort of throw a lot of pieces from other things into it. So you have like table-based methods, you have, again, deep Q neural networks. OpenAI recently released a paper on using evolutionary techniques to train neural networks for reinforcement learning problems, but it's sort of complex and very hard to summarize, and I'm sorry that's not a very good summary of reinforcement learning algorithms. But if you catch me after the lecture, I'd be happy to talk about it more. Any questions about like the sort of separation between these three, or what they would be used in, or I mean, questions about what kind of applications they're actually used for, because some of the so-called applications I've given you are like sort of academic and not actually used in production anywhere. One thing to note is that even though today I'm only really going to go over the supervised learning, in the GitHub repo I'm going to point you at, there are exercises for supervised learning, unsupervised learning, and reinforcement learning, should you feel inclined to go on and read more of them. And if you should feel inclined to go on and look at more supervised learning and try and get really into one of those, I can also help you find resources for that. So any questions about what these are, what they do, why you would care about them, why people get excited about them?
So those neural network algorithms, are they used in every aspect, like the three different kinds in machine learning?
Right. The quick answer is yes. The slightly longer answer is that the most simple neural networks tend to be used in supervised learning. Once you understand how supervised learning neural networks work, it's really easy to sort of, basically for an autoencoder, which is a kind of unsupervised neural net, you just sort of stack two neural nets on top of each other and you have an autoencoder. And then you also use them in reinforcement learning. So yeah, they're used in all of them. They're fairly flexible things. Any other questions? Neural networks are also used in Tesla's autopilot, which is a little terrifying. Okay. So one thing you could ask yourself is, if we want to achieve human level AI, which is, I mean, let's be honest, what we're all interested in at a certain level, which of these would be most important and which of these would be least important? And I could just sort of leave that with you as a question to contemplate. But I'm also going to leave you with a quote from Yann LeCun. Yann LeCun is a professor at NYU and also the head of Facebook's Artificial Intelligence Research Labs. And he said, most of human and animal learning is unsupervised learning, which is fair because most of your learning wasn't from like being told, this is a cat, this is a dog, it's from just sort of looking at the world. But anyhow, if intelligence was a cake, unsupervised learning would be the cake, supervised learning would be the icing on the cake, and reinforcement learning would be the cherry on the cake. We know how to make the icing and the cherry, but we don't know how to make the cake. So that's his quite opinionated take on the issue. So we're going to be doing supervised learning, despite what Jan says about unsupervised learning being most important, on the MNIST data set, which is an old and venerable data set, which isn't really used for state-of-the-art tests anymore because it's pretty good and conquered, but it's a good thing to cut your teeth on. I think it was the last time this was really used. It was basically thick, like basically handled, I think, in the early 2000s. Maybe a little bit later than that. But the best algorithms basically can get, you know, like 0.01% error or something ridiculous like that on this. But we're going to be able to get something which doesn't get quite that good, but which gets pretty good. You should be able to hit like around 80% accuracy with our techniques. So as I mentioned, right, what is machine learning? You write the program, and we're going to be spending a lot of time writing the program. But then we're going to use the data to train the program. That's going to be the data that we use to train it. So what is this MNIST data set? There are 60,000 images of the digits 1 through 9, grayscale 28 by 28, which we will have input as an array of length 784 representing the image. So each element in the array represents a single pixel from the image. It's like the pixel is, if the pixel is white, it's like a 1. If the pixel is black, it's like a 0. If it's a grayscale, it's like 0.5, and so on and so forth. And our goal is to try and say, from this input of 784 length array, what digit the image is, whether it's a 0, a 1, or so on and so forth. And you should try and think about how you could try and do that problem with like conventional programming techniques without machine learning, because it's actually quite difficult to try and come up with some kind of way of doing that reliably. So for instance, you could like try and, like, if you wanted to see if something is a 1, you could see if it has like a lot of pixels stacked on top of each other, but that doesn't really work for like ones which are tilted and so on and so forth. And it also would get confused with 7s and things like that. Hofstadter, author of Gödel-Escher Bach, said that if you could really know how humans classify images, like can read characters and identify characters as characters, you'd have intelligence figured out. And I think he said that like in like the 90s or 80s or something, and he was a little bit wrong. But it's a quite difficult thing to do, ultimately. So what is the algorithm we're going to learn to do that? Actually, before I get onto that, any questions about the problem, like what we're trying to do? Getting some input, some kind of an array, we're trying to output what digit the picture of which the array is a representation is of. Okay. So we're going to use k-nearest neighbors for this. And to explain what k-nearest neighbors is, I'm going to start out with a drawings of some totally different data, which I made with matplotlib in Python. So each of these points represents a piece of data. It represents a piece of 2-dimensional data. We can't put our images on an array on a graph like this, because the graph would have to have 784 axes, because there's 784 pieces of data. The data that we're looking at now, it doesn't really matter what it is. I believe it's of like different kinds of flowers and the lengths of different sepals or something like that. But we can say that this data is obviously grouped in different clusters, and let's say that it's categorized according to the color. So we have like the blue cluster, we have the green cluster, and we have the red cluster. And a different way of phrasing the supervised learning problem is that what we want to do is, given some other point on this data, and given that we don't know whether it's red, green, or blue, we want to try and figure out whether it's red, green, or blue, given what we know of the rest of the data. So given this data, let's use this data to figure out what a new point, whose classification we don't know. We don't know if it's red, green, or blue. What color that should be, or probably is. So one way you could go about this is you could just find the point which is nearest. And if you find the point that is nearest, we could just be like, well, whatever point is nearest, it's probably the same as that. So that's just nearest neighbor. And if we do that, we'll end up with a chart which looks something like this. So this chart has been colored according to whether by the nearest neighbor algorithm, you'd end up, if a new point were dropped somewhere on the map, it would end up getting classified as red, as green, or as blue. And obviously, this corresponds to like sort of what your intuitions about what the classification should be in certain respects. But it doesn't seem quite perfect, probably. The reason it seems a little imperfect is, say, for instance, we have this spot of green up here. But we probably don't want, if a point was dropped there, we might not want to actually say that it's probably green, because this other green point might be like an outlier, and so on and so forth. And so we might not want to, we might want to actually color it red. So we could adapt our nearest neighbor algorithm to be something like 5 nearest neighbors. And instead of finding the closest point to which we are, we could try and find like the 5 closest points and say, well, whatever of these closest points is, whatever is the majority classification of these 5 closest points, then this is what we're probably going to class that point as. Okay, and this too is sort of problematic. because like we have this red point out there in the green zone, and that might or might not agree with our intuitions. But that might give us, I think this gives us sort of a cleaner decision boundary, and perhaps one that corresponds more with our intuition about what a good decision boundary would look like. And so k nearest neighbors is basically just a generalization of this process. We have a bunch of training points, then we're given a new point for which we don't know the classification. We find the k closest neighbors to that point, and then we classify the point to be whatever is the most common of its k closest neighbors. And that's the entirety of the algorithm. Any questions about applying the algorithm in 2 dimensions? Or about the algorithm in general? Okay. So a problem with this is that right now I've been talking about distance and like the closest point, as if that's like there's a clear notion of that. And we do have a relatively clear notion of that in 2 dimensions. But we're going to be dealing with data which is not just on a 2D plane. So the above made intuitive sense because each point could be placed on a 2D plane. But MNIST digits are 28 by 28 grayscale images. So they're represented by an array of length 784, not by an array of length 2. Another way to say that is they're represented by a 784 dimensional array rather than by a 2-dimensional array. So we want to extend our idea of distance from arrays like 1 to 0 to arrays that have arbitrary length. We need to have a notion of distance which applies in any dimensionality. And there's actually a lot of different sort of notions of distance we could use. If you were to take a linear algebra course as sort of a prerequisite to a really rigorous machine learning course, they would get into different notions of distance. For now, I'm just going to sort of explain distance by fiat in arbitrary dimensional spaces. So distance between points in 2D Cartesian space is just the Pythagorean theorem. So it's the square root of the square of the difference between the x values plus the difference between plus the square of the difference between the y values. And what we can do is extend this notion to work in arbitrary Cartesian space by saying, well, it's the square root of the difference between the x values squared plus the difference between the y values squared plus the difference between the z values squared, and so on and so forth until through however many dimensions we have. And we can use that to calculate distance in an arbitrary number of dimensions. And then also we can calculate distance in an arbitrary number of dimensions. We can calculate the closest neighbors and then go on to apply k nearest neighbors. So that's the entirety of the algorithm. And you can go on, the tutorial exercise itself is a pretty detailed guide to implementing it. One question you should ask yourself is, though, what are some potential problems with it? Because k-nearest works pretty well in the case of our digits, the MNIST digits. It doesn't really work very well in any more complex data. The MNIST digits are actually about sort of the limit, the upper limit of the complexity or the dimensionality of the data to which k-nearest neighbors can be applied with any kind of luck. Once you get onto things, bigger images, so if you get onto images that are like 256 pixels by 256 pixels, k-nearest neighbors is no longer going to give you any kind of useful results actually at all. And it's interesting to think about why that might be so. So one thing that k-nearest neighbors does is it sort of ignores global dimensions. It just finds the closest elements. And it sort of ignores overall features. So for instance, if we were writing down a 1, which was like to the left of an image, and writing down a 1, which is a little bit to the right of center in an image. K-nearest neighbors would have a great deal of recognizing that these are similar, even though a human would intuitively be able to recognize that these are very similar. And a little bit more viscerally, training is very fast for K-nearest neighbors because you're just saving the training data. But classification is extremely expensive because classification scales with the number of training examples that you have. And part of the point of machine learning is that you want to just have like a ton of data and throw it at the algorithm and then be able to classify in constant time. So K-nearest neighbors sort of has the opposite of the qualities that we would want for a fast algorithm. Training is fast, but classification is expensive. So yeah. And that's pretty much it. Here is a message, the link. It says, good luck if you're running Linux. That's out of date. I should run fine on Linux now, although if you have any problems, please ping me because I would like to know about it. I just made there used to be an image library which is causing problems for Linux. And so I've refactored that into something else. And I think everything works fine now. But if it doesn't, please tell me. So yeah, does anyone have any questions about anything at all? All right. Well, thank you very much. I hope you all enjoyed this. If you have any feedback, feel free to message me or tell me. I'm always trying to improve this, and it's hard to get. I kind of preferred when it wasn't remote because it was easier to talk with people directly and see where I was being confusing people and where I was not. So yeah, feel free to tell me. And I'm not really sure where FullStack wants you to actually post up the recording, but I will message on the Slack channel once I do. So yeah. So yeah. And I'll still be around for at least a few more hours to help with anyone's questions and so on and so forth. I might be away from my computer a little bit, but I'll try and get to you as fast as possible. So yeah, thank you very much. And yeah.